Hello there and welcome to A-Level Further Maths. Here we're looking at the start of the Volumes of Revolution chapter so we can answer questions from exercise 4a and b. We're going to look at rotating around the x-axis and the y-axis together because it's really important you know when to use which of the two formulas. So for rotating around the x-axis, let's say we have an equation that says y equals the square root of x, for example. What we're going to get you to do in the Volumes of Revolution chapter, you've already seen it in the first year of A-Level Further Maths. You take a limit in between a and b and then rotate this section here, that section coloured in there, round the x-axis to form a three-dimensional shape. This will be the boundary of the rotation, so that will rotate round the x-axis, and what we're looking to do in these sorts of questions is calculate the volume of that revolution around the x-axis, and the shape will actually look something like this. So this part of the curve up here will look like the y equals the square root of x, and that will then rotate round the x-axis, leaving you a volume inside there, inside the blue volume there. So there we are, that's what we're going to be calculating, and the formula to calculate this, an explanation was given in the first year, but the formula that you need to remember is pi integral between a and b of y squared dx. Now you're always going to be replacing the y with what the equation of the graph is. In this case the equation of the graph is y equals the square root of x, so you're going to be replacing y with the square root of x when you go and do those integrals, because then what you've then got is a function of x being integrated with respect to x. It's really important that that happens. Don't try be integrating y's with respect to x's or x's with respect to y's. This is the opportunity for you to input the function into the integral. So that needs to go in here when you do your calculations. And the very similar things happens for the rotating around the y-axis as well. What you'll get here is maybe something like y equals x squared, and that will rotate round the y-axis. And the shape we'll get there will look something like that. If we have limits from a up to b, then it will this curved bit here will look like the y equals x squared graph. And the formula for this is very similar, but it's just swapped around because you're doing it around the y-axis. It is pi times the integral from a to b of x squared dy. Now again, what you have to do here is you have to take your equation and replace x with what y is. So in this integral, it would be integral of from a to b of y dy to work out the volume inside this blue section here. So there we are, those are the two formulas you need to remember. You need to remember when you're rotating around the x-axis to use this formula here, and when you're rotating around the y-axis you need to use this formula here. Now generally what you're going to use for this type of question here is a y equals something equation, and then what you do is you take that something and input it into the y in your integral. But what you're going to prefer to have here on when we rotate around the y-axis is an x equals something to do with y equation, and then you're going to be replacing that where x is in your integral on the volume for working out the revolution around the y-axis. So this integral here is going to be completely in terms of y, and this integral over here is going to be completely in terms of x, and that includes the limits on these integrals as well. This one up here and this one down here has to be like a y equals 4 to a y equals 2, for example, so make sure it's the boundary on the y-axis you're using in this type of integral. So it's not too bad. It's very similar to what we saw in the first year of A-Level Further Maths, but obviously now we know more complicated techniques of integration. We're now going to be getting you to integrate more complicated things. Okay, let's get started in a question then. Let's see how this works in action. So we have the region R is bounded by the curve with the equation y equals sine 2x, the x-axis and the lines x equals 0 and x equals pi by 2. Find the volume of the solid formed when the region R is rotated through 2 pi radians about the x-axis. That's 360 degrees around the x-axis. So this is our little formula we can use to work this out. It's pi integral from b to a y squared dx. So what are b and a first? Well, b and a are going to be the limits. That's going to be x equals 0 and x equals pi by 2. So from 0 to pi by 2. The function that we're working with here is the y equals sine 2x function. So it's going to be sine squared 2x. Generally, you will square the whole function. In this case, it will turn out to be y equals sine squared 2x. Okay, so now we're going to do the integration, and then we need to remember how to integrate sine squared. You integrate sine squared by using a trigonometric identity. Remember, the double angle formula for cos is cos 2x equals 1 minus 2 sine squared x. Let's replace the x in that identity with 2x, and that's what we'll get. We'll get, and then we'll do it again, divide by 2, and then replace the x with a double angle, so it'd be sine squared 2x equals a half brackets 1 minus cos 4x. And it's actually easier to integrate this thing on the right than this thing on the left. So we'll integrate what sine squared 2x is equivalent to. What we'll do is we'll pull out this factor of a half to the front. That just tidies things up inside the integral. Okay, so now we can integrate this. 1 with respect to x and cos 4x with respect to x. That's an easy integral to do. So the answer to this is going to be a half pi, and then it's going to be 1 integrating to x and cos 4x integrating to a quarter sine 4x. And now it's just a case of substituting in the limits. So substituting the limits, substitute pi by 2 in, then substitute 0 in. Everything on this right hand side would just be equal to 0, so it's going to be pi by 2 minus a quarter sine 4 pi by 2. 4 times pi by 2 will be 2 pi, so that will also just equal 0. So it's going to be 1/4 pi squared. Okay, there we are. So it's just basically an integration question. You just need to apply the formula of pi integral from a to b of y squared dx, and you're there in this one. Okay, let's have a look at another similar one. This time we're rotating around the y-axis, it looks like. So the diagram on your left, or on your right in this case, shows the curve with the equation y equals 4 ln x minus 1. The finite region R shown in the diagram is bounded by the curve x-axis, the y-axis, and the line y equals 4. So that's this boundary at the top here, that's y equals 4. The region R is rotated 2 pi radians about the y-axis. Use integration to show that the exact volume of the solid generated is this expression down here. Okay, the first thing we need to do is we need to turn this y equals 4 ln x minus 1 into an equation that has x equals, because what we're going to be using is this formula up here, where we have to replace x with something with respect to y. So we need it to be an x equals formula before we substitute into this second formula at the top here. So let's add 1 to both sides, divide by 4, and then reverse the ln. That will e both sides. So our equation here is going to be x equals e to the power of y plus 1 all over 4. And then when we use this second formula down the bottom here and we're rotating around the y-axis, we're going to be substituting in x for this expression relating to y here, so that we can then integrate with respect to y. So let's do that then. Let's sub in our expression for x, and our boundaries will be the y boundaries between 0 and 4 up here. Okay, so we've substituted in x with what x is equivalent to. You would never be asked to integrate x with respect to dy, because they're two different letters. You must always match up the letters in your integration. So if it's y, your function has to be with respect to y. If it's x, your function has to be with respect to x. Let's expand those brackets. So if we've got a power of a power, we multiply the powers together. And then let's do the integration. Might be easier to write them as separate powers of e, and then maybe factorise the e to the half to the front, because e to the half is just a numerical constant. So now that we've done that, we've got to this point here, and now it's just easy integration. The coefficient on the y is a half, so it's going to be 2e to the y over 2, and then leaving your coefficient to the front, and then substituting your boundaries of 4 and 0. And then when you plug all of that in, you get e to the 4 over 2 minus e to the 0 over 2. Be careful you don't just strike out the e to the 0, because anything to the 0 is 1. So it calculates the values, and here we are. We've got exactly what we're looking for down the bottom here. Lovely, so there we are. So they're just integrations questions really in this Volumes of Revolutions chapter. Later on in the later sections of the chapter we might have to do a bit more complicated working out and constructing of the question. Okay, so it's your turn to have a go at this question here then. Pause the video and give this one a go. Okay, let's have a go at this question then. So the curve of the equation x equals root y sine y is shown in the diagram. The finite region enclosed by the curve and the y-axis is shaded. The region is rotated 2 pi radians around the y-axis. So as soon as we see it's rotated around the y-axis, the formula we're going to use is pi integral from a to b x squared dy, and we'll need our formula for y in terms of x. Oh, that's helpful because that's exactly what we've got. Okay, so find the value of b and then find the volume of the solid generated. So b seems to be this point up here where it first intersects the y-axis again, and when something intersects the y-axis is the x parts that will equal 0. So I'm going to set x equal to 0 in the above equation or formula. So it's going to be 0 equals, and it's going to intersect the y-axis at b, so I could write the square root of b sine b. Now for this thing to equal 0, either this part will equal 0 or this part will equal 0, because the two are multiplied, so either of them can be 0. But when's the square root of b going to equal 0? Well, that's just at 0, isn't it, when b is equal to 0? And it's not equal to 0, so we know that this part is not going to play any part in setting the total of this expression here equal to 0. So it must be the sine b part. And the next time sine is equal to 0 is when b is equal to pi. So there we are, b is equal to pi. Now let's move on to part B, which is find the volume of the solid generated. So as we said before, it's going to be this formula up here. So I'm going to start with that then. So it's going to be pi between the boundary of pi down to 0 of x squared. Now that's what we're going to do here, is we're going to take this expression here and square it. So it's going to be y sine squared y dy. Now what we'll have to do here is we'll have to split up the sine squared, and the sine squared will have to be replaced with its double angle formula equivalent. So that's going to be y, and then it's half minus a half cos 2y. That's its double angle formula equivalent, which is much easier to integrate. Let's expand the brackets and maybe move that constant factor of a half to the front. So it's going to be y minus y cos 2y. Now the first part of this will be nice and easy to integrate. Y, with respect to y, that's just going to be a half y squared. So my answer here is going to be half pi, and then it's going to be in brackets half y squared. Now the second part here is going to be more difficult to integrate. Let's move that part over to the other side, and we'll put it in between the boundaries of pi and 0. So how do we integrate this y cos 2y here? Well, that's going to have to be integration by parts. Y will be the part of it that we differentiate to 1, and cos 2y will have to be the part of it we integrate, which will be a half sine 2y. So then, let's calculate the integral of y cos 2y with respect to dy. That's going to be, so what do you do first? You do u and v multiplied together, so it's going to be a half y sine 2y, and then minus the integral of these two multiplied together, that would just be a half sine 2y with respect to dy, and then that will equal half y sine 2y minus, the integral of sine is negative, so that would be a plus a quarter sine, cos 2y. Okay, there we are. So let's now put that inside here, but it was minus onto all of this first, so it would be minus half y sine 2y. No, but all of this is halved, actually, the half's still at the front, that's fine. So it would be then a quarter cos 2y. Okay, so now we'll be working out the answer to this. Hold on, let's just group off that and we'll put it all down here. So it's going to be half pi, and then putting pi into that, that would be a half pi squared. And putting pi into this, that would be 0. Putting pi into this, cos 2 pi is equal to 1, so that would be plus a quarter. And then putting 0 in, that would be 0. Putting 0 in, that would be 0. Putting 0 in, that would be minus a quarter. And then simplifying all of that, the quarters will cancel out. So it would be 1/4 pi cubed as the answer to this question here. So there we are. That's the answer to question from page 81, question 4. So there we are. We had to do a little bit of integration by parts in this section here, but then the main integral for what we were working out here was down this left-hand side there. So there we are. So make sure you have plenty of goes questions from exercise 4a and 4b. Make sure you need to know what formula do you use when you're rotating around the different axes. And yeah, thanks very much for watching.